Today you are going to learn about transforming trig functions such as y equals sine of x or y equals cosine of x. We're going to do all of this with sine of x. The only difference is going to be your parent function for cosine. So initially, we're going to take a look at graphing y equals the sine of x. So thinking about what your unit circle tells you, if I had a picture of the unit circle, I'll just do a quick little sketch up here. I have this point here, which is the point, of course, 1, 0. Which means when I have 0 degrees, my sine, remember, the sine is always the height, the y value, so my sine is 0. So now I don't have a scale on my axes, so let's maybe put a scale on here. Let's go up to 1, count by quarters then, down to -1, and we'll count all these by pi over 6. So I'll go ahead and fill those in. So then as you've practiced graphing the sine function on your sheet of paper, you have all of the values in between. So you have at pi over 6. So at pi over 6, this marker right there is up at a half. And then at pi over 3, your sine function is up at the square root of 3 over 2. A decimal approximation, not the nicest. At pi over 2, however, it's at 1. And now I'm going to kind of skip some of those in-between ones. I know over here at pi, my sine is 0. At 3 pi over 2, it's -1. And at 2 pi, it's 0. So what I did is I did one complete cycle. Again, trying to think of what my key points are along the way. The more points that you put in there, the better your curve is going to be. Now I know I can keep going multiple times around my unit circle. So here again at 0 is 2 pi. And then halfway between 2 pi and then this over here is 3 pi is going to be my max value. So my max value occurs up here at 1. So halfway between those. At 3 pi it was 0. And then halfway between 3 pi and then over here now is 4 pi. Halfway between those is my min value, so down here at -1. And then over 4 pi it's 0. So what I did is I created now 2 cycles. One cycle fits between 0 and 2 pi. And my second cycle fits between 2 pi and 4 pi. And then it keeps going. I could also go in the negative direction. So from here, it's going to cross through technically until it hits that min value and goes around. So this is what your typical sine function is. It has different key characteristics. So if you take a look at this, you know some different pieces to it. So let's take a look at some of these pieces that we know, some of the graphing characteristics, for instance. So some of the graphing characteristics, take a look at your x-intercepts. So I have an x-intercept here at 0, 0. I have another x-intercept over here, which is at pi 0, and at 2 pi 0, and at 3 pi 0, and at 4 pi 0, and at -pi 0. So generically, all of my x-intercepts occur pi units away, or even you could say 0, plus pi n. What that means is the number of times we add pi to it. So again, 0, start that at 0 instead of having to do pi. 0 plus pi n. Again, n is the number of pi's you are away. And it could be negatively. N could be negative, could be a negative pi away, comma, 0, because your x-intercept, your y value is 0. Y-intercept is not nearly as complicated to write. How many y-intercepts are there? 1. So your y-intercept occurs at 0, 0. Let's look at our domain. For your domain, you're taking a look at what all your x values are. Are my domain values restricted? Could I have every possible x? Yep. Therefore, it's all real numbers for your domain. Now let's look at our range. Can I have all possible y values? Nope. Take a look at where your maxes and mins fall. There are multiple maxes and multiple mins. However, the highest y value you ever reach is 1. The lowest y value you ever reach is negative 1. Therefore, y is going to be greater than or equal to negative 1, but it has to be less than or equal to positive 1. Again, I did talk about there are multiple max values. So I have a max at pi over 2. I have a min, at 3 pi over 2, and then that happens every 2 pi later. It just continues to repeat. It's max every 2 pi. So these are some of the graphing characteristics of sine. The graphing characteristics for cosine are just slightly different, but you are going to have those multiple x-intercepts. You're going to have one y-intercept, and then think about what you know about your domain and range. Since your cosine graph is just a translation of your sine graph, domain and range are just shifting left and right. No up and down shifts, so therefore domain is still reals, range is still between -1 and 1 inclusive. So now we're going to start taking a look at performing some transformations. So this is just all sine information you already know, but we need to know this in order to do our transformations. So these are the 3 different transformation pieces we're going to look at for graphing these. So we're going to graph and write the equation for a graph shifted 3 units up. We're going to graph and write the equation for a graph shifted 2 units to the right. And we're going to graph and write the equation for a graph vertically stretched. Again, all of these are for our parent function, which is y equals the sine of x. So here's the graph of the sine of x. So if I'm going to shift this entire graph 3 units up, that means this whole thing is going to shift upwards 3 spots. So if I use what I have here, I'm going to take every single one of these points and shift them up 3 places. So if I do that, I'm going to be quite a bit off the graph because, for instance, this point that's at 0, 0, now is going to be at the point 0, 3, which is way off my graph. So now instead I'm going to have to change my x-axis so that instead of counting by quarters, I have to take into consideration the fact I need to move this 3 units up. So I'm going to have it count by 3s. So in order to do that, I now have that first tick mark at 1, the bottom tick mark at -1. So in other words, now it counts by 1, so I should be able to shift this 3 units up without a problem. So if I'm going to take this point that was, according to my parent function, at 0, 0, it's going to shift 3 units up, so it's going to go up to 3. And then think about how the graph was. So the points that were at, it started at, I had a y-intercept of 0, 0. Has another x-intercept at 0, 0. It has an x-intercept at 2 pi 0. It has an x-intercept at pi 0. It had a max at pi over 2, and it had a min at 3 pi over 2. So every single one of those points shifts up 3 spots. So we had the one that shifted up here. So now my max value that was at 1 already now has to go up to 4. And then my 0 spot goes up to 3. And then my -1 spot goes up 3 spots, which only takes it up to 2. My 0 spot, therefore, goes back up to 3. So what this does is it shifts my entire graph upwards by 1 unit. Now I can keep repeating this cycle. As long as you think about the fact, I'm going to draw this in. Please don't think it has anything to do with the actual graph of it. It just is a location. It shifted my x-axis 3 units up. We call that a midline because it's in the middle of the graph. So by just doing that, it helps me in turn go, okay, so I know from this midline, now it's going to go up to my next max. So over here is up to my next max, and then it comes down to my midline. Then it goes down to my min, then it comes back up to my midline. So every 3 boxes in essence, because it's all every pi over 2, it goes up and down from that midline. So I'll just delete that midline. And now I can connect the dots. And you guys can putz around with this a little bit on Desmos to kind of see what happens to each of these graphs along the way. Because now we need to be able to write an equation for this. This was y equals the sine of x. Since I shifted it 3 units up, is that your x value or your y value? It's your y value. Since it's my y value, it can't be directly attached to my x. So I'm going to put x in parentheses here because I know that's what's happening with my x, whatever's in those parentheses. And that's what I'm taking the sign of. So I'm not taking the sign of this shifting up because it's attached to this y. In order for it to be attached to that y, it's a plus 3 on the outside. Okay. After you get through this video, go around, kind of putz around a little bit with Desmos, have it graph some of those shifts for you. That way you can make sure that you have a pretty easy understanding of what each of these does. Now for the second transformation, now we're going to shift left or right. Since I'm not shifting up or down, I can leave my scale like I had before as quarters. So now since I'm shifting left or right, I'm shifting left or right, in this case 2 units. Now this is kind of odd because my horizontal axis counts by pi. It's counting by pi over 6. So, which is decimal approximation. So you've got to figure out approximately what 2 is. So I can kind of start going through and dividing each of these out. So I know first off, it has to be less than pi, because pi is obviously 3.14. So then I can start looking at what each of these are. So I can figure out, okay, well, what's half of a pi? Well, since pi is 3, half of pi is going to be less than 2, so I know it has to be greater than this. So this is 1 pi over 6, 2 pi over 6, 3 pi over 6. So if you type in 4 pi over 6 into your calculator, you end up getting just over 2, like 2.09. So it's just over 2, which means I'm going to have to shift it just a little bit less than 4 pi over 6, which is 2 pi over 3. So it's just going to be a little bit before that is how I'm going to shift it. So I drew a little mark on the bottom so I know where everything is going to be shifted to approximately. So now every single one of these points moves 2 units to the right. So this point that was on my y-axis shifts just 4 units to the right. And not 4 units, excuse me, 4 tick marks. So that 0 value is going to go here. So every 0 value is going to shift 4 units to the right, or 4 tick marks to the right. But so is every max. So I just did this first point. Now my max shifts just 4 units. So right about there. And then I had this midline. And then my min. And my midline. From my midline I go to my max. And then my midline. And my min. Gotta find out I didn't do that one very well. And that one's off my graph a little bit. So from here, when I connect these dots, it's going to come up from there. I'm going to get rid of the other graph that was here before. And I have my graph. Now, keep in mind I shift everything 4 units to the right, so I all of a sudden have this hole. Do I really have this hole right here? No, because it can keep going to the left. So I'll follow this pattern back out. So from my midline, figure out how far over your next value is going to be. So from my midline, it's going to come down to my min value. Keeping in mind there's 3 boxes between there. So here's my min. So it's going to come down here, and then for my min, it's going to go up. So that's how you can get a full graph shifted 2 units to the right. Shifting to the right, does that affect your x or your y? Think about what you know about that. Whenever things are affecting your x in this case, it's going to be attached to x. And when it's attached to x, it's always the opposite. So since it's moving it 2 units to the right, this is going to be x minus 2. Okay. Again, start kind of putzing with some horizontal ones in Desmos as well, just to make sure that you are comfortable feeling those horizontal shifts. Then the last one that we had, so now when we graph this vertically, again, I'm going to go off my paper, so I'm back to a scale of 1 vertically. I'm going to have to take all of these values, and I'm going to have to like pull my maxes up to the top and my mins down to the bottom. So in essence, what this is going to look like is it's going to do something along the lines of this. Please know that's not perfect by any means. But it's going to pull up my tops and pull down my bottoms all along this midline. So it's that multiplier. So for this one, it might be easier to write the equation. Is that going to affect my x values or my y values? if it affected your x, it would have to be inside those parentheses, but it doesn't affect your x. It's going to affect the y values. So maybe I'm going to put a 2 in here. So my vertical stretch is going to be a multiplier of 2. Now the nice thing with these is we have all these 0, 0 values. So 0 times anything is 0, which means every single one of these is going to sit right on my x-axis. They don't move anywhere. But then this value that was up here at a 1, my max value, multiplies by that 2. And you know what, maybe, yeah, that's fine. Multiply it by 2. So that max value now goes up to 2. And then another max value over here, so that goes up to 2. But my min values that were at -1 multiply by that 2. So -1 times 2 is -2 and -2. And connect. And now you have your sine function stretched. So you just took those y values, you multiplied them by that 2, and now you got a vertical stretch. So now what we're going to do is we're going to put all of these back together into one equation. So if you take a look at what each of our equations looked like. A vertical shift, added that 3 at the end. A horizontal shift, added or subtracted that value inside, remembering that it's the opposite operation. And then a vertical stretch is that number out in front. Therefore, the general equation for all 3 of these transformations would be y equals a times the sine of x minus h plus k. So we only did each of those individually. We didn't put them together. But we did at least work on each of them along the same axis, or along the same path. There is, however, one more transformations that trig functions have that none of the other functions that we worked at did. And that deals with a change in one of the pieces that you saw when we were doing the blood lab. So if you think back to the blood lab, we did 2 different transformations. The one we did was this vertical stretch, where based on where I let go of it, that's where it spread the tops and the bottoms of it out. Okay. Additionally, depending on what speed folks walked, that brought in a new transformation that we haven't seen before. And that was that horizontal stretch or compression, which will be represented with, we will call our period. So it's based on what the cycle length is. So for instance, in our parent function, in order to complete one cycle, it goes out to 2 pi. So we say the period for sine is 2 pi. Again, period representing how long it takes to get through one complete cycle of your graph. So now we're going to look at, well, what happens when our period isn't always 2 pi? How do we figure out what that does, and how does that affect our equation? So based on that, we have a story problem. This one comes directly from your textbook. This is problem 7.126. So if you get stuck on this, feel free to read through that section. In 7.126, we're talking about an air traffic controller. She watches the radar, which is like the radius of the circle, going around her screen time after time after time. She figures out that it takes 2 seconds for the radar line to travel pi over 6 radians. So she decides to make a graph in which the input is the time. So the input this time is not going to be my radian measurements, because she says she knows it takes 2 seconds for it to get to pi over 6. So 2 is going to represent that pi over 6 increment. And then her outputs is going to be the distance from the outer end of the radar line to the horizontal axis. So it's kind of like our x-axis, just like it was before. So we can start by graphing this. So again, since she said pi over 6 took 2 seconds to get to, at 0 it starts at 0. And then 2 seconds, it would be that pi over 6 length. So then at 4 seconds, it would be 2 pi over 6, that height, I should say. At 6 seconds, it would be 3 pi over 6's height. And you know that the sine, because this is what we're taking a look at, we know that the sine at 3 pi over 6, at pi over 2, is the max value. So at 6, it's up here at 1. And then I can keep going. So now what I look for here is Another 6 seconds later, so at 12 it's at 0. Another 6 seconds later, at 18 it's at -1, because it's 1 unit down from that horizontal. At 6 seconds later, at 24 it's at 0. So there's one complete cycle. So therefore, I know that it takes 24 seconds to get all the way around her circle so that she can see what it is. So now, what is the period for this? How long does it take to get to all the way around my circle? It's from beginning of the cycle to the end of the cycle. From the beginning of the cycle to the end of the cycle, it took 24 seconds. So the period for this problem is 24 seconds because it took 24 seconds to complete one full cycle, which in turn is going to affect our equation. So 24 seconds. So that 24 seconds is how long it's going to take to get to the whole thing. So usually the period for sine, is 2 pi. However, we're going to now introduce this b value. This b value is going to go right in between the sine of x. That b value is actually what controls your period. So period is going to now become 2 pi divided by b. Because b is going to break it into however many cycles it's going to need, however many pieces it's going to be in order to hit that full cycle, which is its period. So we said the full period was 24 seconds. So 24 equals p. So to find that b value that's going to go into your equation now, and multiply both sides by b. So 24b equals 2 pi. Divide both sides by 24. B equals pi over 12. So that's how it's breaking it down horizontally to deal with this stretch factor. Because before, our stretch was 2 pi, which is 6 point blah, 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 to finish an entire cycle. Now, in order to continue or to finish an entire cycle, it's going to take 24 seconds. So in essence, you can think of this as stretching horizontally because of that multiplier of 2 pi. So the general equation for the 4 transformations for y equals the sine of x is y equals a times the quantity of, a times the sine of b times the quantity of x minus h plus k. This b does sit outside of the quantity. That b in turn is part of the sine function though. That b is your angle. So if this was my problem from before, my equation would look something like y equals sum a times the sine of pi over 12 times x minus h plus k. So this is going to give you what each of your pieces are for your 4 transformations. If any of this is confusing to you, which for some of you, you might struggle a little bit with it, here's what you can do. What I just went through is 7.2.1 and 7.2.2. What you can now do is you can go back and work through those problems to see if you can figure out what I did along the way. I just did a shortened, condensed form of that, putting some verbiage to it, adding in a few additional pieces. So at this point, if you are struggling with those, go back through those sections and work through those problems. The excuse of, I can't do it, is unacceptable. So I showed you one way. Now you can go back and use your textbook as your resource, or if all else fails, you can do YouTube searches on transforming sine graphs.